Hope you all had a great lunch and are ready for more information. Thank you for your interest in wanting to learn what we do at Netflix. So let's get started. My team at Netflix is responsible for building the ingest pipeline for all the events that are generated within Netflix. And we're also responsible for offering some sort of stream processing functionality as well, and we build that infrastructure. So I lead the team that deals with the stream processing infrastructure. So earlier this year, Netflix went global, and it became a truly global and world's largest internet streaming service. Our service is, there we go. We have over 83 million subscribers in over 190 countries. They access our service from 1,000 plus different kind of devices, and we account up to 35% of downstream internet traffic. So that's a lot of movies being streamed by users. And it's over 125 million hours of video every single day is being watched in the world. I don't know if people have time to do anything else, but it's good for us. This amounts to over 1 trillion events being processed by our pipeline every single day, and over 1.4 petabytes of data is handled. We do peaks of about 10 megabytes a message, 16 megabytes a second, 43 gigabytes a second of peak bytes that are flowing through our system. And our average is about 4K per event. And we do all this with 4 nines of availability on the pipeline. Our events have steadily grown exponentially over the last couple of years by orders of magnitude. And we've had to evolve our processing pipeline as well to handle this load. We've gone through 3 iterations of it, and now we're at the cusp of building the next round of things. So the last pipeline that we switched out, we did it without any downtime, and we did it while making sure that the data diff between the old pipeline and the new pipeline was less than 0.1%. So that's comparing 2.6 petabytes of data every day before we swapped it out. And we're going to do a similar thing with our next generation of the pipeline. So several years ago, it started very simple. I don't know if anybody is familiar with Apache Chakwa. It's a defunct project right now. It's not being used anymore. And it evolved into this, a hairy Hailbar mess, very difficult to manage and maintain. And this is what my team inherited about a year ago. And this is what we built. So in a broad structure, what my team owns is 3 big pieces. One is the messaging piece, the stream processing piece, and the management piece that helps manage the infrastructure across these 2 layers. The messaging piece is mainly Kafka right now, and we have a very large Kafka cluster deployment and brokers that we have. I won't go into a whole lot of details on the messaging side. What we'll today focus on is the stream processing side of it. And our philosophy is to enable and create Duplo-style reusable blocks so that our customers can use these blocks and deliver value and build their applications really fast. So this is what we ended up deploying and simplifying the whole architecture compared to what you saw a few slides ago. Simple producers, simple sinks, and in between we take care of the rest for our customers. They don't have to worry about it. It's declarative. It's defined using a self-service UI. So this is what the UI looks like. The user comes in and creates a new data stream. We provision the Kafka topics for them. They come in and configure which sinks the events flows to. So for example, in this case, they've configured Elasticsearch going to Hive, and they've specified a declarative filter, and that goes to another Kafka cluster. The one thing here is all this is specified by the user, and then we take care of deploying it and provisioning it. The user also automatically gets a dashboard for their stream, and there's a whole bunch of metrics that I haven't shown here. But every single user gets what's happening on the producer side, any drops. We have alerts for drops if the drops are more than 1%. and the routing, what's happening at each stage of the routing. So they have complete visibility into what's happening. And we take care of the infrastructure. So any lags in routing events to their sinks gets us paged, or we have automation to take care of it and scale it up. So this is what it looks like internally. The whole thing runs 100% in the cloud. There's nothing in the data center. It's 24/7 uptime, and as you saw, 4 nines of availability. And anytime we have a region failure in Amazon, or a data center failure, or if you've heard of chaos gong, or when we move traffic, we automatically take care of that failover event traffic as well on our side. So let's look at how the event flows in our pipeline. The event starts its life in the producer. We have our own thin wrapper around Kafka that gives us functionality to change routing of events to different Kafka clusters so that we can do failover even at the Kafka layer. And we have a bunch of integrations with the Netflix ecosystem for service discovery, metrics, and other such things. The producers can also produce using a proxy layer for non-Java based applications that want to generate events. Those events get into our fronting Kafka cluster, and those go on to our router layer, and we'll get into detail into this, what it is. And based on the sinks they configured in the UI, we'll send the events to Hive, Elasticsearch, or another Kafka cluster. All the events in Netflix go to Hive today, and about 30% of it go into Elasticsearch and the Kafka clusters. The reason we have separate fronting Kafka clusters and the consumer Kafka clusters is so that we can guarantee high availability on the Kafka clusters on the front end. If you didn't do that, then we could have a large fan out on the consuming side, and it'll be very hard for us to predict the deterministic availability of the clusters. So we separate them out, we isolate them. So let's dig a little bit deeper into the routing layer. So currently the routing layer is implemented using SAMZA. The reason we chose it at that time was a couple of reasons. One was the time constraint. We had to get this new system up and out and running, and everything was new. Kafka, the runtime environment, the routing stuff, everything was being built from scratch. So we wanted to minimize risks, and SAMZA offered very good Kafka integration. We had to put in a few fixes to make it work at our scale and in containers. But otherwise, it was pretty smooth sailing for us from that regard. Now, one thing to really understand is the use case that it's being applied for is a massively parallel use case. What I mean by that is in Kafka, you have partitions. And if a router is processing, let's say, 5 partitions, and your topic is 100 partitions, if that job fails, you don't want the other partitions to be stopped from being processed. The other thing is they're pretty much stateless, these jobs, except for the checkpointing offset that needs to be stored. And we use another Kafka cluster, checkpointing Kafka cluster, to store the checkpoints so that we can offer at least once semantics. Our routing infrastructure is built using Docker, a bunch of C, and custom runtime that we built. So the self-service UI you saw puts the information in a MySQL database. Every single host instance has an executor process. This is very much similar like Mesos, but we have taken a lot of the extra moving functionality or pieces and then trimmed it down. So we have a very simple architecture. So the node agent is the process that runs on the host. Every minute, it reconciles with the database to see if there are any new jobs it needs to run, any job configuration has changed, and if it has changed, it automatically relaunches it. And the reason we use Zookeeper is first time the host wakes up and the executor connects to it, it assigns itself an ID. So this way, we can guarantee that one and only one job ever runs in our whole infrastructure. Versus in a Mesos-style environment, which we'll go into later, there's a possibility of a split brain, and you can have 2 jobs running. And that's why we need the highly available configuration for Flink, which we'll get into in a bit. So the general flow is once the jobs start running on the host, based on the config in MySQL, it starts processing data. And every time it processes an event, whether it needs to be filtered or some projection needs to be applied on it, Then we checkpoint it once the processing is done. This is a little more detail into what I went on. Some additional stuff we did was we aggregated the logs from all these containers that are running on Docker. And we created tooling so that you could stream the logs not only from the live container, but from the logs that were backed up to S3. So you could say, give me the logs for the last 10 hours, and if half of those logs were on the host and the rest of them on S3, it seamlessly stitched it. And we had tooling around it to do that. So yes, there's no Mesos and no Yarn. It works just with MySQL and it scales fine. So we have 4,000 Kafka brokers that are running in total across 27 clusters in 3 different regions. And we have 14,000 SAMSA jobs running in 14,000 Docker containers. And this is the largest deployment of Docker containers at Netflix, or at least a year ago anywhere that we knew of publicly. And these jobs run on over 1,600 C4 extra large machines. So what the system does is it offers at least one semantics. It's multi-tenant. The runtime execution environment you saw launches jobs for all the different topics or data streams that are being configured. It's self-service. We took a look at this couple of screenshots. It's really scalable, of up to 1 trillion events per day, and it's fault tolerant. The architecture behind the fault tolerant is more like the actor system. The node agent kind of acts as a supervisor, and if one of the jobs dies, it'll resurrect it again. So we have pretty good fault tolerance on that. And we also use the fault tolerance as a way of upgrading the jobs and doing things like that. We keep our event payload immutable. We wrap it in our own custom wire protocol, which is opaque to the producer and the consumer. The reason we do that is so that we can support multiple serialization formats, multiple encoding schemes along the way. We also inject metadata to help us with the event deduping and to know where those events came from, like GUID, timestamp, host, and app. And these are in our headers, so these don't actually go into the payload unless the user asks us to inject it in the payload. And that only happens when we push the events out into the sink. So every once a week, we do cluster failovers using a tool called Kafka Kong that we built. So we intentionally route production traffic to a different cluster, and we fail over the other cluster to see that we are available. And we've had a couple of occasions when we had to seamlessly switch traffic, and it was less than 0.1% of data loss, the worst that we saw. So I think that's something that's been critical for us to achieve the 4 nines of availability and less than 1% of drop on a regular basis. And this auto-scaling happens based on historical traffic. It's not true auto-scaling currently. It's a process that runs out of band, observes the historical traffic, and adjusts the job configuration so they are sized accordingly. So it's not true auto-scaling from within the routing itself. It's external right now. So where are we headed next? This is not in production yet. We are vetting it out in production, though, in staging. And so I'll share details with you about what we're doing here. So we already offer kind of stream processing as a service, but the processing is very limited. All you could do is filtering and some projections, right? We have needs for being able to offer much more sophisticated stream processing, but at the same time, people don't want to maintain all the infrastructure that goes along with it. Currently, we've seen people use other streaming engines, and the way they build the infrastructure is 90% of their time is wasted in the infrastructure, and only 10% they spend on business logic. So we want to take that 90% overhead and build it out for them. So this is the effort to do that. So we want to offer multi-tenant support for stateful streaming apps. And we would like to do it for multiple stream processing engines, but right now we're going to start with Flink first. We also want to have support for schemas. And of course, we want to expand the self-service tooling. So at a very, very high level, like a 50,000 foot of what happens is a user creates a job, let's call it an app for data analysis. And they could do one of two things. They could either write their custom logic and offer us a jar or some other packaging mechanism, or they could write some kind of a DSL where they could specify what their job looks like. Like Stream SQL is one that we heard about today. And so users specify their job in either one of those two ways. We take that and we deploy it in Docker containers running in our container runtime environment, which is auto-scaling as well. And out of the box, we also are going to offer dashboards, metrics, and ease of managing their life cycle of the jobs. Let's say I want to upgrade my job. I want to change the versions. What about changing the versions of the infrastructure itself? So all that kind of tooling, we're going to take care of it. So we looked at Beam, and most of you may be familiar why you end up using Beam. For us, it offered like a portable API layer, but still it has sophisticated semantics to build really useful applications on top. It's been the ideas behind it has been solid. It's been under development for several years at Google under Millville, Flume Java, and Dataflow APIs and concepts that have been around. So initially, we were thinking about running Beam and running Flink at the same time. But what we realized is there's significant effort involved in getting the Flink infrastructure up and running for our scale. And plus, we were also moving to a new runtime environment called Titus. It's a Mesos-based container runtime. So we wanted to simplify things a little bit. So we're going to do an iterative phase build-out. Plus, at Netflix, we try to deliver business value really fast. So just trying to build Beam and Flink at the same time would have taken us much longer to achieve that goal. So first, we're going to take Flink-based processing jobs and run them on our Titus containers. And once we have successfully done that and we're confident in the infrastructure, then we'll start layering additional abstractions on top of it, like Beam. Plus, I think the streaming side of Beam needs a little bit more time. We started this effort about 3 months ago. And so I think Beam's going to evolve as well. Once we are ready, I think Beam streaming will be ready as well for our specific needs. So let's take a quick look back at the routing layer and what use cases we are targeting with Flink. So there are 3 use cases we are targeting with Flink. The first one is the massively parallel use case that we talked about. The second one is there's a bunch of merging, unmerging that happens and partitioning that happens to get the data into Hive. And at Netflix, the way our Hive infrastructure work is we don't have HDFS. We use S3 as our storage layer, as the distributed file system. And we have adapters for HDFS so that we can use S3 for it. And what this demux and merge is talking about is you could get events that are muxed from across different topics, but all those need to be demuxed into their own tables and into hourly partitions. So right now, that logic's sitting separately in a separate app. We're going to bring that in to the router layer. And we also have routers that just route to Elasticsearch, which would remain. So those are kind of the 2 use cases. And we also want to do delooping while we are sending events to Hive. The third is more custom development. We have a use case for a complex dynamic session windowing, and it has pretty much quite a bit large state as well. And we want to do some kind of counts, and at the end of our session window, which is quite large as well, we want some accurate results out of it as well. So this is where we think Flink, we can leverage Flink for its checkpointing and windowing and the other semantics. So this is just revisiting the massively parallel use case. You have different partitions. You have different consumer groups consuming from it. If, let's say, partition 3 or consumer 2 is down, you still want to continue processing consumer 1. So this is how it looks like, the deployment of Flink on our Titus container environment. It's a typical highly available deployment for Flink. We have a zookeeper, we have a standby job manager. If it fails, it can take over. And we have a bunch of task managers that are running inside Docker containers. And the difference here is we run all this infrastructure in VPC. And so what we can do is every Docker container gets its own IP address associated with it using ENI. And so we don't have to worry about port mapping and things like that. It just works like we have a separate host where it's running on. So it simplifies a lot of deployment options for us. So this is how the internals of Titus looks like. We have a separate team at Netflix that works on this. And if you want to know all the details about it, they gave a QCon talk earlier this year, and you can look that up. So we leverage Fenzo, which is the scheduler and offers auto-scaling semantics on it. It supports Docker containers. It has log aggregation. So it's an enhanced version of what you saw before that we did with Samza. And this wasn't available when we were building our previous architecture. So now it's built. We're going to deprecate the old one. So I'll run through a few screenshots of the Titus UI and the UI that we use and the dashboards we use for this Flink program. So this screenshot shows you all the jobs that are running on the Titus runtime environment. We have something called Spinnaker, which is a continuous deployment and delivery system. And you can see the clusters that are launched here. This one is about 11 host that it's running on, and it's about, I think, 96 slots. It's running 96 slots on it. So this specific example, we took a large topic, around 500 megabits per second, and about 2,000 Kafka partitions, and we fed it with real production traffic to see the behavior. And so we have metrics around consumption, syncs, how many records are going in and out. So the graph on the right top corner kind of gives you an idea of if things are balanced across the cluster. If all of those lines converge with each other, then you know it's pretty well balanced. If they go out of alignment, then you know there's some problem with balancing of workload in the cluster. We capture Kafka internal consumer metrics as well to know things like lag or if it's taking too long to fetch messages because of variability of message sizes. It tells us if you have to tweak any of the configuration parameters or not, and we alert on these. These are just some internal metrics for task managers and job managers. So I think one thing what we did here is currently the metrics has scopes assigned to it, the metric names. And one enhancement that we're looking there is to expose those as tags, as key value map pairs. So it makes it easier for us to integrate into our internal metric system. We have an internal metric system called Atlas, which is what we're using. But having just the string scope format, we had to parse it and parse the individual pieces out to see what host it's running on and tag those accordingly to our metrics. So there's some checkpointing information, checkpoint sizes. Okay, so naturally we got curious to see what it did performance-wise. And we had the same topic being routed to another Kafka cluster from Samza, and we had a similar one for Flink. Now, just a few notes of disclaimer. These tests were done specifically on our runtime environment for a specific use case, for a specific kind of data. So if you try to repeat it, you may not get the same results. You may get different results. So this is the part we are doing a perf test on. It's the massively parallel use case where the events are flowing from the producer, and they end up in another consuming Kafka cluster, which is the consumer Kafka cluster here on the right. They're completely different runtimes, as you might have seen. And so we're focused on net outcomes rather than looking at it from a white box perspective and seeing what's happening at each stage, because it's not a real apples to apples comparison. We just want to see at the boundaries what's happening. So this is just a repeat of the slide just to get the context back in. The state is backed up by S3 currently, the way the job's set up. So we observed 17% cost savings running Flink for that specific job, 16% better memory utilization, 40% better CPU utilization, and 10% better network utilization. And as you can see, the message throughput is quite a bit better as well. So we are awaiting some of the Flink features so that it lets us put this whole infrastructure into production. And our first priority there is to get this large-scale 1 trillion events per second running on Flink routing layer. So fine-grained recovery is one. What happens today is if one of the task manager dies, the whole job gets restarted again. And for massively parallel use cases, you get these blips because you don't want the rest of your partitions from being stopped from being consumed, right? So with fine-grained recovery, just the task manager that went down would be brought up and the processing would start again. It wouldn't impact the rest of the jobs. And that's captured in flip 1, I believe. Checkpointing and save pointing related enhancements. Unifying the checkpoints and save points, today they're kind of different. So what we ideally want is we want the checkpoints to happen periodically, which are now called periodic save points automatically, so that if you have a failure, you have something to start back from. And the checkpoints would be persistent. And earlier this morning, we heard about the compatibility of being able to resume our jobs across Flink versions, which is important to us as well. And we want to build some tooling around being able to expose what's in a checkpoint, because several times we've seen we want to debug and we want to see what's happening inside the checkpoint state, but it's hard to look inside. And we want to make it easier for a user so that they can look inside and see what's happening. The other one is we want to be able to atomically issue a save point and a stop so that the job's not progressing after that. Because if you don't do that, then it's possible that you won't be able to resume from the exact save point that you left off at. The other one is dynamic scaling so that we can resume a job with a different parallelism. Until we have true auto scaling, this helps us relaunch a job with a different parallelism if the overall traffic on the topic has changed. And job elasticity as well will help with the auto-scaling part of it. Now, with the auto-scaling, there's a configuration for network buffers, which relies on how many task managers are running and how many connections there are. So today, it's a statically configured value. It would be nice to have that automatically configured when we are scaling the task managers up and down with the job elasticity. Because otherwise, it's that one piece that doesn't let you auto-scale. The cluster management and elasticity. So our integration with Meso-style runtime environment, we want to be able to ask for more resources if you are scaling up, or relinquish resources if you're scaling down. So the enhancements here will help us build that abstraction for us. And having additional window function metadata will help us shed some light inside what's happening and expose metrics around it. And we want large state support because the use case 3 that I mentioned is going to have a lot of large state. And so recovering from failures would take that much longer if the state's larger. So the incremental checkpointing and hot standby should definitely help with that functionality. So these are a bunch of features that are kind of nice to have. We don't need them right now to go into production. Triggered DSL was one, but as we heard, it's done already. I didn't know that. I just got to know today morning, which is good. And the other one, really important one for us, is the side inputs and outputs, because we have a need for joining slow changing data with the existing event stream, and to also kind of feed back into it with the side outputs so that we can handle late data and support late semantics, eventually with like retraction or accumulating or other kind of semantics. So one thing that I'd really like to leave you guys thinking about is we've been using stream processing engines for doing data analytics, right? Can we really use them beyond just that? Can we use them for building non-analytics applications that still look like streaming? So one example is, let's say you have a large video transcoding environment, right? and you want to encode as fast as you can. So let's say you're chunking your movies into smaller pieces. And now each piece, you're doing some kind of processing in it. At the end of it, you're merging it. You're generating metadata around it. And you're computing metrics over it. You're looking at what's happening in real time. So some applications like this that we've seen, if you have the right kind of infrastructure, stream processing engines could enable those new kind of applications to be built on top rather than building your own custom applications on it. So I think Flink has that potential. There are some kind of applications that could fit into that model. So you can not only use it for streaming and data analytics, but you can actually use it for building applications. There's a lot more information that's available if you want to read through our evolution, how we run our Kafka clusters, and the stuff we did with Samza, the stuff about Titus, and all our open source projects. So I think you'll open it up with that for questions.
Hi. So you mentioned Keystone is multi-tenant.
Right.
So how do you manage like quotas and resource allocation across the different jobs? Like, do you do different?
Right. Right. So we kind of approach it from two directions. One is we look at what the existing event traffic is. Let's say if it's an established event traffic pattern, then we know how much resources it needs. And the way we do deployment, if it's a Titus-like environment, it offers CPU isolation, network isolation, and memory isolation. So we ask for a certain number of resources. We say, give me 2 CPUs, X amount of memory, and it manages those isolations. You don't go over it. Now, how do we compute how many resources we need? That again comes back to the event traffic that's flowing in. Let's say you have 100 megabytes per second. And we say we don't want to lag more than 2 seconds. We want to be up to date with what's happening in the event side. So based on that, we can compute how many containers we need and what resources we need in each container. So what we do is we look at each container when we are testing all this out and trying to determine the sizing of it. We look at each container size. We look at the footprint of the stream processing engine that's running. We look at the memory overhead it has. And we kind of find a upper bound on it. And so for each stream processing engine, like Flink has a certain footprint, Samza has a certain footprint, and so we have a baseline established for that. So with that baseline and taking the event traffic and taking the lag, we currently have a component called Job Manager that does exactly that, and it tweaks and relaunches the config when it thinks that it's time to scale it up.
Then thanks a lot.
Okay. You get your 6 minutes back.